The discovery of antibiotics is one of the most important advancements in clinical medicine and public health. It's laid the foundation for a number of other advancements, including the ability to perform surgeries more safely and the reduction of infant and maternal mortality rates. Many antibiotics are derived from either bacteria or fungi. For example, penicillin, which is secreted by the fungus Penicillium, can kill bacteria. This is because microbes use antibiotics to fight off other microbes. But the use of antibiotics, and more broadly antimicrobials, which include medications that target not only bacteria, but also viruses and fungi, has exploded in recent years. Antimicrobials have been used on an industrial scale, partially because of overprescription in humans, but more so because of routine use in farm animals. In fact, a good number of antimicrobials are excreted from humans and animals unchanged, and these get flushed into wastewater, which allows pathogens to be perpetually exposed to antimicrobials. In response to this enormous selective pressure, many pathogens have become highly resistant to antimicrobials. Now, when it comes to bacteria, generally speaking, there are 4 mechanisms for how they become resistant to antimicrobials. The first mechanism is antibiotic inactivation, or modification, which is where bacteria develop specific enzymes that destroy and inactivate antimicrobials. One example is beta-lactamase, which is a bacterial enzyme that destroys antimicrobials that contain a beta-lactam ring, like penicillins and cephalosporins. As a result, bacteria that produce beta-lactamases are immune to the action of many beta-lactam antibiotics. The second mechanism is the alteration of a target or binding site. An antibiotic that can't bind anywhere is rendered useless. One example is a methicillin-resistant Staphylococcus aureus, or MRSA, which modifies its penicillin binding locations, making them unable to be bound by any antibiotics in the penicillin family. The third mechanism is by bypassing metabolic inhibition. For example, some antibiotics, such as sulfonamides, disturb the metabolic pathway that synthesizes folic acid, which is vital to DNA-based organisms. But to get around this, some bacteria are able to scavenge for folic acid from the environment, completely circumventing the action of sulfonamides. The fourth mechanism relies on preventing antibiotic accumulation. One way that bacteria do that is by decreasing the permeability of their membrane to the antibiotic. The other way is to create efflux pumps, which pump the antibiotic out of the bacteria. Both actions result in lower intracellular antibiotic concentrations, which reduces or even negates the effect. Now, these mechanisms work in different organisms against different antibiotics. It's an ongoing challenge. For every new antibiotic that's identified, pathogens rely on selection pressure to find a mutation that somehow allows them to thrive in the presence of that antibiotic. Alright, as a quick recap, bacteria can achieve antibiotic resistance through 4 fundamental mechanisms. Inactivation physically destroys the antibiotics before they can do their job. Alteration of the binding site leaves the antibiotic without a binding site, and therefore unable to work. Alteration of the metabolic pathway completely bypasses the activity of the antibiotic. Finally, reduction of accumulation keeps the intracellular levels of antibiotics low.
Beta-lactam antibiotics, like penicillins and cephalosporins, have a beta-lactam ring in their structure, which gives them their name. These medications inhibit cell wall synthesis in bacteria. Unfortunately for us, bacteria are becoming increasingly resilient to beta-lactams, So we've come up with non-beta-lactam medications to inhibit cell wall synthesis. Now, to overcome these resistances, we've found ways to inhibit cell wall synthesis at multiple stages. So our body consists of multiple eukaryotic cells, while bacteria are prokaryotic, meaning they're primitive, single-cellular organisms. Most have a slimy capsule made out of polysaccharides and a cell wall which encapsulates and protects the bacteria like a suit of armor, and offers structural support. Bacterial cell walls are made of a substance called peptidoglycan, or murein. Peptidoglycan is a molecule composed of long strands of aminopolysaccharides running in parallel. These are made of segments of N-acetylglucosamine, or NAG, and N-acetylmuramic acid, or NAM, in an alternating pattern, so NAG, NAM, NAG, NAM, and so on, like a pearl necklace. At the tips of and protruding from the NAM subunits are tetrapeptide and pentapeptide chains. These peptide chains can link to other peptide chains from the neighboring strands through a process known as transpeptidation. This is carried out by an enzyme called DD transpeptidase, or penicillin binding proteins, or PBPs. Now, these enzymes are like locks, and there are specific binding areas for the pentapeptide keys to fit into. Once the key goes in the lock, the PBP enzymes fuse them together, creating a stable link between the two aminopolysaccharide strands, and strengthening the cell wall. In essence, all beta-lactam antibiotics, like the penicillins, somewhat resemble the tetrapeptide chains. Inside the bacteria, PBP enzymes will mistakenly bind to the beta-lactam antibiotic molecule, instead of a tetrapeptide, and stick inside the PBP forever, like putting chewing gum in a keyhole, permanently disabling it. As more and more PBPs get disabled, the cross-linking fails to happen, and the wall becomes weak and unstable. If the affected bacteria attempts to divide, their cell wall will collapse, killing them in the process. Now, some bacteria have developed resistance to beta-lactam antibiotics. The most notable is the notorious Staphylococcus aureus, which evolved to have enzymes called beta-lactamases or penicillinases that break down the beta-lactam ring within the antibiotic, rendering it ineffective. In response, though, we started adding beta-lactamase inhibitors, like clavulanic acid, that would bind to beta-lactamases and inactivate them, again like the gum into a keyhole. Another approach was to create new kinds of beta-lactam antibiotics, like methicillin, which has a large side chain that wouldn't fit into the keyhole of the beta-lactamase. These did work pretty well, until some Staphylococcus aureus developed PBP site mutations that changed the shape of the keyhole. So even if beta-lactamase enzymes can't break down these antibiotics, they won't fit into the PBP enzyme and thus won't work. We call these bacteria methicillin-resistant Staphylococcus aureus, or MRSA. This poses a huge problem, because it makes MRSA virtually untreatable by beta-lactam antibiotics. To treat MRSA, we resort to so-called reserve antibiotics belonging to the glycopeptide antibiotics, like vancomycin and teicoplanin. But even that might come to an end, as MRSA is also developing vancomycin resistance, becoming VRSA. We want to make a simple and fun mnemonic that'll help you efficiently memorize the medications that work on each of these stages. So first we can use bacteria carrying wheelbarrows for the transport proteins that move NAM and NAG across the cell membrane. Next are the bacterial security guards, which represent the beta-lactamase enzymes. They're protecting the bacterial masons, which are the PBPs that build the cell wall. Finally, we have the wall itself, which is under construction. Our first class of medication is the bactoprenol inhibitors, like bacitracin. It works by blocking bactoprenol phosphate, which is the transmembrane transporter embedded within the bacterial cell membrane. It lets NAM and NAG molecules cross from inside the cell membrane to the outside, where they're needed for the synthesis of peptidoglycan. Once the transport protein is inhibited, new peptidoglycan can no longer be made. Bacitracin has a very narrow spectrum and only works against a few gram-positive bacteria like Staphylococcus aureus, Staphylococcus epidermidis, and Streptococcus pyogenes. And even then, it only works topically. meaning it's used to treat skin and eye infections by rubbing it onto the affected area. They're never to be applied intravenously or intramuscularly, as they're highly nephrotoxic and can lead to renal failure if used for systemic infections. Alright, so back to the mnemonic. For this class of medication, we're attacking bacterial cell membrane transport proteins represented by the wheelbarrows. Let's have a basilisk, representing bacitracin, attack them. These bacteria are purple, since bacitracin works on common gram-positive bacteria that stains purple. Let's have it shed its skin, because this medication is for topical use only, for treating certain skin infections. Next, let's look at how we can overcome the beta-lactamase problem. One way is to shut them down with beta-lactamase inhibitors. Members of this group include clavulanic acid, tazobactam, and sulbactam. These medications play a supportive role and are given with beta-lactams like penicillin. Once inside the bacteria, they bind permanently to the beta-lactamase enzymes and disable them, which allows the penicillins to do their work. However, they're more effective against gram-negative bacteria since gram-positive bacteria like Staph aureus often have PBP mutations that render the penicillins ineffective. These combo medications often have their own names, like Augmentin, which is a combination of amoxicillin and clavulanic acid. Again, back to the mnemonic. Let's look at the bacterial security guards representing the beta-lactamases. We have an erupting volcano to represent clavulanic acid, and a police officer with a baton to represent tazobactam and sulbactam. Together, they're enough to scare away the security guards. Notice some are pink, since gram-negative bacteria stain pink, and the rest are purple for the gram-positive bacteria. This clears the way for the penda with a pen, our symbol for penicillin. Next are two groups of beta-lactam antibiotics that have a slight twist. First are carbapenems, which include imipenem, meropenem, ertapenem, and doropenem. They bind to PBPs and inhibit cell wall synthesis, just like penicillin. However, the twist is that they possess a modified ring structure, so instead of a sulfur atom at position 1, they have a carbon atom. This tiny change makes the beta-lactamases unable to bind to the medication. Carbapenems are considered to be more potent than the beta-lactams. Their spectrum is wider and they cover most of the gram-positive and gram-negative bacteria as well as anaerobic species. With the exception of ertapenem, carbapenems are notably useful against Acinetobacter species, which cause nosocomial infections like ventilator-associated pneumonia, and Pseudomonas aeruginosa, a bacteria so hardcore and resilient, it swims laps in hand disinfectant just to wake up in the morning. These medications are only used when other antibiotics fail, since they have severe central nervous system toxicity and could cause seizures. Imipenem is rapidly broken down in the kidneys by tubular dehydropeptidase. To make things worse, the metabolites are also nephrotoxic, and that's why it's used with cilastatin, which inhibits the tubular dehydropeptidase. The other beta-lactam medication we'll talk about are the monobactams. The only member of the family that's currently used is aztreonam. Unlike the other beta-lactams, their beta-lactam ring is not fused to any other ring, and it's sticking out on its own. This makes them resistant to beta-lactamases, as they can't fit properly inside them. They're very effective against gram-negative bacteria, like Escherichia coli and Proteus species, as well as the dreaded Pseudomonas aeruginosa, but they're completely ineffective against gram-positive ones. Aztreonam is well tolerated and has few side effects. Once again, back to the mnemonic. For this scene, we have the two groups of beta-lactams that are directly assaulting the bacteria mesins representing the PBPs. First, coming in from the bottom, is a lone Amazon warrior for aztreonam. She's only attacking pink-colored mesins because it's effective against gram-negative bacteria only. She's also throwing a spear at a Mona Lisa look-alike representing Pseudomonas. Next, flanking from the top, are the carbapenems, which are represented by a squad of carb-rich penne pasta soldiers. We have them attack second because they're used after other antibiotics have proven ineffective. Leading them is their emperor, representing imipenem. He's carrying a celery scepter because we need cilastatin to prevent breakdown of the medication in the kidneys. The army is attacking both purple and pink Masons since they're effective against both gram-positive and gram-negative bacteria. One of their main targets is the other Mona Lisa lookalike, and she's holding a fishbowl to represent anaerobic bacteria, and a large cinema ticket for Acinetobacter. But it's highly unlikely that she'll make it to the movies this day. Now, one of the pasta soldiers is shamefully tap dancing away from the Mona Lisa. He represents ertapenem, the only carbapenem with no effect against Pseudomonas. War can be grim, and some of the pasta soldiers are lying on their side, with their head chopped off and twitching. This will help you remember the severe cerebral nervous system toxicities that could lead to seizures. The final family of medications is the glycopeptide antibiotics, like vancomycin, telavancin, and teicoplanin. They inhibit cell wall synthesis by latching onto the tetrapeptide chains, preventing them from being linked by the PBP enzyme. Glycopeptides do not act on the PBP, which allow them to bypass the PBP mutations that make MRSA so resistant to beta-lactams. However, some Staphylococcus aureus have evolved to have a D-lactate at the tip of the tetrapeptides, so glycopeptides cannot bind to them. Some of these strains have partial resistance and are called vancomycin intermediate Staphylococcus aureus, or VISA for short. Strains with complete resistance are called vancomycin-resistant Staph aureus, or VRSA. Glycopeptides are most often used to treat gram-positive bacteria that are resistant to other medications. They can't be absorbed in the GI tract, so they're typically given intravenously when treating systemic infections. Per oral vancomycin can be given to treat GI infections like Clostridium difficile. Adverse drug reactions include thrombophlebitis, ototoxicity, nephrotoxicity, and so-called red man syndrome, which is caused by diffuse flushing. Back again to the mnemonic. We're now looking at the wall and we have 3 vehicles representing these medications. There's a van with a mouse logo for vancomycin, a van with a TV logo for telavancin, and a police or cop plane for teicoplanin. Now, these medications act directly on the molecules that make up the cell wall, so let's have them crash into it. The wall itself is purple to represent gram-positive bacteria. And let's put some barbed wire on it because glycopeptides are used to treat infections that are resistant to other medications. Toppling off the wall, there's a closet for Clostridium. And on top of that is a Mars rover for MRSA. For side effects, let's use the driver of the van who's running away from the vehicle. He's dressed in a red ninja outfit to represent Red Man syndrome. He's wearing headphones that are blasting loud music for ototoxicity. And one of his legs is covered in bulging blue veins for thrombophlebitis. He's also holding his injured flank as he hobbles away to help you remember nephrotoxicity. Alright, as a quick recap, let's look at a mind map that'll help organize the information we covered. Multiple families of cell wall synthesis inhibitors are created to combat the ever-increasing resistance in bacteria. Bactoprenol inhibitors like bacitracin inhibit the transport proteins that move NAG and NAM units across the cell membrane. Beta-lactamase inhibitors like clavulanic acid are used to disable beta-lactamases, and they need to be used in combination with other beta-lactams like penicillin. Carbapenems like imipenem and monobactams like aztreonam are beta-lactam antibiotics with slightly modified structures. This makes them impervious to beta-lactamase degradation, so they can inhibit PBPs. Glycopeptides like vancomycin bind to tetrapeptides that make up the cell wall. This allows them to bypass bacterial resistance based on PBP mutations. They're mostly used for dealing with highly resistant bacteria like MRSA. But wait, there's more. Here's a mind map with all of the mnemonics from the video. Go ahead and pause the video so you can test yourself to see what you remember. And stay tuned for the answers at the end.